So hello everyone, welcome to the first lecture of Language of Chemistry, and I'm Anik Ghosh with you, your chemistry teacher. Today we are going to discuss about the topics that you can already see in the board. That today we are going to start with the introduction towards this chapter. After that we are going to go through the matters and the classification of the matter, the atoms and the theories of the atoms, and then in the end we are going to discuss about the Dalton's atomic theory. So all these things are very interesting, and we are definitely going to go through some cool videos as well. So stick to the video till the end, because in this video we are going to learn so many things today. Okay, so before we start, I think we should know about the history, about the discovery of that. I think we have already heard that there are so many scientists, those who are involved in this discovery of atoms, but the entire process started with some philosophers. So I think you've heard about the Indian philosopher Anik, who discovered about who just told us, gave us the idea about the atom or Parmanu in the time of 500 BC. I think you can understand, like they got the idea about this atom from very beginning of the era. Now after that, there was, you can see over here, British chemist John Dalton in 1800. The exact year was 1808, when he just gave his entire theory of atom. Now, he was the scientist, the first scientist who who just told us about the nature of the atom and what is an atom. He just told us some postulates. He just gave us some postulates, those we are definitely going to discuss in this video. After that, what happened is, you can see over here, this is Ernest Rutherford. So just after, sorry, this is J.J. Thomson. So just after John Dalton gave us the idea, the postulates about the atoms. After that, in 1904, it should be like 1904 was the date when, was the year when he gave us the model of the atom, the atomic model. The first atomic model. It was 1897 when J.J. Thomson was the first scientist who discovered about the electrons and proved Dalton completely wrong. So we are going to discuss about the postulates of Dalton, and there I'm going to tell you where J.J. Thomson proved Dalton wrong. That is a very good story behind this. We are definitely going to go through that. After J.J. Thomson, there came Ernest Rutherford. Okay, so after that, Niels Bohr. Okay, so all the scientists were involved. After the Heisenberg, after that Sommerfeld, and in the end it was Heisenberg. So there were so many scientists who were involved in this entire process. But let me tell you one more thing, interesting fact about this, that most of them were the physicists. Starting from J.J. Thomson and John Dalton, after that Rutherford, after that Niels Bohr, all of these scientists were just physicists. None of them were chemists. And the beginning was done by the philosophers. So far, we haven't introduced any of the chemists in the entire history of the discovery of atom. So I think this was the entire timeline, how the entire the models and the discovery of all these things happened. So we will start with this very interesting video about the matter. So as I told you, that like all these scientists, all these philosophers had the same idea, that if you just keep on breaking a matter into the smallest possible particle, then the smallest particle that would be left is an atom. Okay, this was the preliminary idea about that. Now, in here, we are just going to discuss about the different states of matter, different types of matter, and their atoms. So just stick to this video, and this video is very interesting. Okay, so give your full attention to this video. This is an atom. Okay. Monday, Sally, Gary, and Larry, all of them to the science lab now. So this is what Atom is thinking about the friends, his friends. So he's just thinking that Sally, who is a solid, is very strong. And if you're talking about Gary, he doesn't have any shape, right? It's just like a ghost, right? You can see, like they're in a science lab. Just give me a moment. They are in a science lab, and right now the atom is looking at a bottle. Okay, and the entire bottle, you can see, entire bottle is made up of just the atoms, which looks the same, and just like they are made up of that thing only, right? There is having very little space between. So you can see all the atoms are, arranged in such a way that they can have the closest distance in between them. This is called packing. So all the atoms tries to pack themselves in such a way that they can form a proper lattice. Or lattice is a very, technical word here. So they can form a proper shape. I should rather say. Okay. So they are making, all these atoms are making a plastic bottle. So all this matters, all these atoms are, packed in such a way that they are giving a shape to a solid. So they are making a plastic bottle, which is a solid. That's why you can see the spaces in between two atoms are very less, isn't it? This is the state of matter. So it's almost everything in the world is a matter. There are types of metal like Gary and Anik, like Gary. This is very important for you. Matter is anything that has a mass and takes up some spaces. Okay. So like you can see all these three things have a mass and they can take up some particular spaces, isn't it? So now they're talking about mass. So as I told you, all the atoms have a particular volume and a particular mass, right? Now what is mass? So mass is something that the amount of matter present in a bottle. If we are talking about a bottle, the amount of matter present inside the bottle. Okay, if we're talking about ourselves, so when we are just standing on a weight machine, so in that moment, the thing that we are calculating is our mass only, right? Because the value we are getting is not our weight. Okay, just remember one thing: weight is the amount of attraction power or the inward pull given by the center of the earth. Okay? So that is a completely different thing. It changes from one place to another place. But the amount of mass present in a body is a fixed value. Okay, a fixed quantity. So mass is the amount of a substance present in a body. Okay? Now they're just talking about volume and a mass. So let me tell you what was the main idea behind this entire video. So yeah, the first thing is just remember one thing. We have matter is mainly is divided into three states. One is solid, another one is liquid, another one is gas. So there are three types of matters mainly. Okay. So in your books, you may be able to find that there are two other types of matters are also there. States of matters are also there. One is plasma, and the other one is Bose-Einstein condensate. So condensate. So these two things are very rare. Okay. So plasma, I think you can understand, like this is a terminal state of matter. So when you are heating a matter in with a very high temperature, it is getting into converting into itself into a plasma, right? Like we see for the lava and all, right? And BC is a Bose-Einstein condensate. To find this thing is like its longevity is very low, okay, very low. It's on near about a micrometer, microsecond or picosecond. But recent research has come out that if you just try to make this Bose-Einstein condensate in the space, then it may stay there for 1 second. So I think you can understand like, getting these two states are very difficult. Okay. Now, coming back to our discussions over here. So there are totally 5 types of matter, but 3 are the most important: solid, liquid, and gas. But how are they different than each other? They are different by the word intermolecular spaces or separations. I should rather say spaces. Now you try to tell me from where are these spaces coming? Definitely they are generating from intermolecular forces of attraction. Intermolecular forces of attraction. So all these type of intermolecular spaces are coming out from the intermolecular force of attraction. If the attraction force is more, then definitely the space is going to be less. If the attraction force is less, then definitely the space is going to be right. So that's now this intermolecular force of attraction has a name. We call it van der Waals. We call it van der Waals force of attraction. Okay, we call it van der Waals force of attraction. So, with respect to this van der Waals force of attraction only, the matter is classified into 3 types of things. If the van der Waals force of attraction is more, then definitely it is going to be solid. If the van der Waals force of attraction is less, then definitely it is going to be liquid. Okay, and it's very less, then it is going to be the gases. And apart from that, what we have learned about the matter. Okay, so what is matter? We have learned is matter is amount of mass. Okay, the amount of mass present. I think so far you have understood everything. There is no such problem with that. Now coming to the next part. Okay. Now, before moving on to the next part, there is one more thing we need to know. That is about pure substances and mixtures. So what are the pure substances? Definitely all the elements are together only. There is no such new elements inside that. So that is called a pure substance. And what about the compounds? What about the impure substances? We could rather say that there is a particular ratio of everything. Like let's consider that H2 is there. H2 is the compound. Okay, that is 2 is to 1. H2 remains in 2 is to 1 formation, right? So, so to justify the entire formation of this compound is going to be very difficult, right? So for that reason only, I'm asking you that the pure substances are like elements or compounds. So this is also a type of, you can see this is a compound is not a pure substance, right? Pure substance is something that contains only one type of molecule or one type of element, right? That is a pure substance. Apart from that, what is in the mixture? There are two types of mixture as well. One is homogeneous, another is heterogeneous. So homogeneous is when you just mix every particles together, and okay, so homogeneous is not about the particles getting together. I should rather say is the concentration remains okay. So the concentration remains the same all over the concentration remains the same all over the solution. Okay. But for heterogeneous, it is not there. Okay. Now we would be talking about the classification of a matter. So yes, we were about to discuss about the classification of the matters. Now here you can see the matters are of two types. So it can be pure substance or it can be a mixture. So from the name itself, you can understand the pure substances are the elements of the the substances that is containing only one types of elements, isn't it? Just look at it. Like pure substances over here, what are the examples? You can see what are the different types of pure substances that can be there in the nature. So you can see there is element and the compound. If we just think about both of them, about the elements or the compounds, both of them, you can see the pictures over here. They are just the pure substances, isn't it? If we are talking about the elements, then elements are, if I just talk about carbon, if I just talk about, let's say, diamond or graphite, let's just talk about graphite. Now, the graphite is only consisting of carbons, isn't it? It is only consisting of carbons. So definitely there is only one type of element present in there, only one type of species present in there. So for that reason, definitely it's going to be a substance which is pure. Now, what about the compounds? So if you just take another example to understand this compound, let's just take water for an example. Let's just take water for an example. If water is a compound, now if you just take a glass of water, then definitely it is, I don't have to tell you that all the molecules are there inside the glass of water. It's only H2 only, right? There is no such other molecule inside it. So all of them are H2O. So a glass of water is made up of only one type of molecule. So for that reason, we can say that both of them are pure substances only. Clear? Now, what about the mixtures? So definitely the mixtures are something like if we just take two pure substances together, at least two pure substances together, and if we just mix them together, then definitely we are going to get a mixture out of it. Now, you can see we can get two types of mixture. One is homogeneous, another one is heterogeneous. You can see this one is homogeneous, this one is heterogeneous. So what do they mean by these names? Homogeneous. Now you try to understand it. Homo means same. And this word genius is coming from the word genity, from which means the concentration. Now, if I tell you, if we just take a bucket full of water, okay, and let's just consider that I have mixed a few spoon of some kind of coloring agent in it. Let's just say I'm mixing some amount of rust in there. Okay, I'm mixing some amount of rust in here. If you don't if you don't know about rasna is something like it's like a syrup. Okay, I think you know about syrups. So this is just a syrup in it. Now, if you just mix it and if you just stir it, then the syrup particles would be all over the places. Now, if you take one glass of syrup from here, and if you take one glass of syrup from here, and if you're mixing the entire thing properly, then definitely both of them would taste the same, isn't it? So the A beaker as well as the B beaker, both of them would taste the same. Why is that? Because the syrup particles are equally distributed throughout the solution. So can we say the concentration of the syrup particles are equal throughout the solution from wherever we take it? So the concentration of the syrup particles is same throughout the solution. Clear? So this is called a homogeneous solution. So whenever you mix some salt or sugar in a glass of water, you're getting a homogeneous solution only. And one more thing about homogeneous is you won't be able to see the solute particles in there, isn't it? If you just mix some sugar in the solution in a water, okay, so you won't be able to see the sugar particles in it, isn't it? So that is how we get to understand about that. Now what about the heterogeneous solution? Try to understand. Heterogeneous solution is something where definitely the concentration of the solute particles won't be equal in all the places, right? So the concentration of the solute particles would be different. Okay, so if I just let me just share the screen with you again. If you just come back over here, so for the heterogeneous solution, if you just look into the picture, you'll be able to understand it. Like for the homogeneous solutions, you can see the solute particles are equally distributed. Whereas for the heterogeneous solution, you can see some of the particles are over here and some of them are over here. So they are just, they are not properly, we can say properly stirred, or they are not, properly distributed throughout the system. So these type of solutions are called heterogeneous solution. So let me give you an example of a heterogeneous solution. So let's just take, for an example, you can write it over here, sand in water. If I just mix sand and water together, so I'm talking about a heterogeneous solution. If I just mix sand and water together, they're never going to get mixed properly, right? So definitely what would happen is you'd be able to see this situation only, isn't it? The sand particles, let's just consider these are the sand particles. They would settle downwards. And the water particles over here, you can see it. The water particles, these are the water. Okay, so the water particles will be all over the systems. So they are, they are not getting mixed equally. So what would happen is we call it a heterogeneous solution. So if someone asks you, what is air? What do you think about air? Would it be heterogeneous or homogeneous? That's a very good question, isn't it? Because if you are thinking that it is homogeneous, then also there is some, let me tell you the answer properly. As you cannot see any particles inside the air, so definitely it is a homogeneous solution, isn't it? Because there are so many gaseous particles in the air. Like there are oxygen, there are carbon dioxide, there are nitrogen. There are so many gaseous particles inside the air. So if you cannot see them, as we cannot see any particles, right? If you just look into the air surrounding you, you won't be able to see any of the gaseous particles in here, right? So definitely we can say that the air is a homogeneous solution. But right now, whatever we can see right now, this is the homosphere of our atmosphere, isn't it? When we are moving on to the heterosphere, then definitely there the concentration of the particles, the concentration of the gases are not same in all the spaces, right? In all the places, right? So there we can say the air is heterogeneous in there. But if someone asks you what about the air, so that's an ambiguous question over here. I think you got the point, right? So this was the entire concept about this. Now we would just look into a cool video about the atoms. and I would definitely describe the entire video like I did for the last one. So let's see this video now. It would take a little time. Just wait for a moment. Now we are going to understand about atoms, okay? Taking a little bit. Okay. So I would like to stop this video over here only, the first part only, because they're saying that atoms are very tiny particles and we cannot see them. And let me put some more information over here, because the atoms are, how small are the atoms? Atoms are 10 to the power minus 9 meters, that we call 1 nanometer, isn't it? This is how small an atom is. Okay, so definitely we will not be able to see them. Okay. Everything is made up of atom, right? So we're watching all the, yeah, they're just trying to tell you how much atoms are there. So over here, they're just trying to tell you that the atoms, look, according to John Dalton, as you remember in the first part, we were discussing about how the atom structure were built from the very ancient time. So what happened is, in the 1808, there was a scientist whose name was John Dalton, who gave us the idea about the atom, isn't it? And he just told us, if you just take a piece of matter, if you just break it into the smallest particle, then you'll be able to find atoms from it, right? Now, what I want to say is, after that came J.J. Thomson in 1897, who just proved John Dalton completely wrong about his this postulate, because we are going to discuss about John Dalton's postulate in the next video. But for now, we can say that John Dalton was proved wrong by another physicist called J.J. Thomson, because John Dalton was the one who believed that the atoms are the smallest particle in the matter. But actually, what happened is, in the matter, inside the atoms, there are subatomic particles. There are subatomic particles. And there are 3 types of subatomic particles. All of them were not being discovered by J.J. Thomson only. J.J. Thomson discovered only electrons, but there were protons and there were neutrons as well. So electrons, protons, and neutrons, these 3 are the subatomic particles present inside the atom. Okay. Yes. Nucleus is containing protons and neutrons, and you can see the electrons are coming like that. The neutrons in neutral and electrons and electrons. So as they are, so definitely they are attracting each other like the solar system, right? And it's attracting the Earth. So they're just talking about the mass and sizes of them. You are going to, we are going to go through the exact values of masses, right? For electrons in 9.1 into 10 to minus 31 kgs, and proton and neutrons have near about same masses, 1.675 and 1.6725 into 10 to the power minus 27 kgs. So we are going to discuss about those values in details. For now, they're just giving you an idea overview that the protons and the neutrons are almost having equal masses, but the electrons are, they're about 2,000 times lighter than the protons. Okay. Near about 1836 or 37. You can say any of the values. So the mass of a proton by the mass of an electron gives you a value of 1836 or 1837. You can say any one of them. Okay, 1836 or 1830. So it's now near about, we can say 2000. Near about 2000 times. If you just round it up. Okay, near about. That's why they are writing much less. That is what the 1000 times like. The size of the atom is the radius. So they are saying that 10 to the power minus 10 meters, and I have written near about 10 to the power minus 9. So yeah, there are atoms. Those are 10 to the power minus 9 meters, 10 to the power 10 meters. So you can say like they are in the order of nanometers only. Okay, so 0.1 nanometer or 1 nanometer, whatever it is. That all the things they are trying to tell you is the combined discovery of all the scientists. So the atoms have the neutrons and the protons inside the nucleus, and the nucleus is the center. Okay. Now all the electrons are revolving around the nucleus. Got it so far? They're saying that the nucleus is very small with respect to the entire atom. So let me tell you the exact value. It is near about, it's like 10 to the power minus 15 meters. This is the size of nucleus. Okay. If the the radius of the atom was 10 to the minus 10 meters, in the order of 10 to the minus 10 meters, then the order of nucleus will be 10 to the minus 15 meters. So let me be clear to you. This is 1 lakh times smaller, isn't it? Is 1 lakh times smaller than the entire atom. So the entire atom is so small and very small, right? And the nucleus is even 1 lakh times smaller than that as well. Okay, I think you can understand how small a nucleus is. I'm trying to make it a little bit visualizable to you. If the atom is near about the sports arena, then the nucleus is near about a P in the middle. Okay, so I think you can understand the comparison between them, right? The electrons are revolving around. Like over here. Green ones are the nucleus, and other things are hydrogen, oxygen, and sulfur. So you can see in the each shells, the electrons are revolving around with a specific amount. Now there is a rule which is setting the idea, which is giving us the idea that each shell can contain only a particular number of electrons. Okay, so that is called 2n square rules. From there, 2n square rules. So from there, we can understand like each of the shells can accumulate how many number of electrons. Okay, so that was the overview. So this was the entire overview. We are going to go through all the steps, all the things in a step-by-step manner, how it got discovered, how the atomic model came. Okay, so we are going to discuss about those things in detail. So this was the entire overview about the atoms. So atoms are the tiny particles. Even there are subatomic particles inside that only as well. There are called electrons, protons, and neutrons, and we have discussed about their masses and about the nucleus and the outer nucleus regions. Okay. Now I'm going to tell you about the first theory, about the atoms. This was the entire overview of the atoms we have just gone through so far. Now I'm going to tell you how did we came to that conclusion. How did you know that the atoms looks like that? So let's just go through the entire timeline, like the entire scientific world went at that time. So I am just dragging you down to 1808 when there was a scientist called John Dalton who gave us the first atom theory. Now let's just look into this video. Just give me a minute. It would again take a little bit of time. So this thing you already know, right? He was an English scientist and he was known for that thing. You can see they're talking about elements, compounds, and mixture. I want to call, right? The matter whether element or compound or a mixture is made up of tiny particles, and you can see the atoms inside of them. Like some of the atoms are basic and all, right? Like all the atoms of the given elements are identical in size and the mass and the chemical properties. This was the first postulate given by John Dalton. So the first postulate was like all of them are made up of some tiny atoms. This is the building block. He just called them the building blocks. Okay? Building blocks of what? Building blocks of matter. All the matters around us. Okay. And the second postulate was you can see all the atoms of the given elements are identical in size, mass, and chemical properties. All the atoms of a particular element all the atoms are identical. I'm just writing identical because you think I can understand that by the word identical is they have all the things in a similar way, right? You can see two iron atoms are over here. They have all things in same size. They are just tracking a balance over here to show you that they have both of same chemical properties. As I told you, they have same chemical. Again, coming to the third point, atoms of different elements or different molecules have different chemical properties and different mass. So definitely from this line only we can understand that. So if the atoms are different, if the atoms are of different elements, then definitely the atoms are of different elements, then definitely their size and mass and so all the properties are not identical, right? All the properties won't be the same, right? What's this? So you can see they have different sizes, different thickness, properties, different physical Here they're just trying to show you. Okay, that's right. We have different sizes. Exactly. They're going to show you that they have different masses as well. So again, the balance curves. So you can see sulfur is not that much heavy as the iron, right? You expected it. The different chemical properties. Now I think they are going to talk about atoms are indivisible particles and that would be enough. Okay. So the thing was about these were the postulates of Dalton that they are the tiniest particles, they are the smallest particles, same elements have same types of atoms, different elements have different types of atoms, and they have different chemical properties, different physical properties, sizes, masses, everything is different, right? Now, atoms are the one. Let me tell you, like in a chemical reaction, you cannot destroy or create any atoms or any of the masses. So the thing is, in the chemical reactions, atoms are the only one that those are reacting on the first place. So if a chemical reaction is occurring, then definitely with respect to the collision theory, the atoms are the one who are colliding with each other to give you that reaction. So I think that's it for today. I think you have understood all of it, and I think we had fun for today's class. And one more thing, there are so many other there is so many upcoming classes for this chapter out there, so you just go through all of them, and if you have any doubts, I think you know what you have to do. You just have to write it on our forum, right? So that's it for today. Thank you, everyone. Have a good day.